Right. This is for Jason. Number one, Jason, the reason you cannot run a MANOVA is because your DVs that you are considering mental health between the Beck anxiety and the Beck depression scores is they're not strongly correlated. If they were relatively strongly correlated, in other words, if somebody scored high in anxiety, they would be also highly depressed, then it would make sense to lump them under the same umbrella and turn them into one giant DV. But because they do not correlate strongly, right? The correlation is 0.143 and it's not significant, then it makes no sense to do that. So you're not going to run a MANOVA. And then in other words, you're not going to put the DV for mental health as a combination of the anxiety and the depression scales. And then for the physical scales, same thing, right? White blood cell count, high blood pressure, cholesterol, there's no significant correlations in there, so it doesn't make sense to lump them together.
Isn't there a correlation there?
No, the significance. Exactly. Yeah, see, I keep reading the same numbers, right? You got to look at the significance. If this number isn't less than 0.05, it doesn't matter what the correlations are. Okay, so what we did was we ran a t-test between those that identified as stressed and those who were not. Here's all the descriptive means and everything, but we don't really. We're just going to look at the t-tests. So we're going to look at the significance level of the T. Okay, don't look at the F. That's something different. It's related to, but it's a little bit different. You're going to look at the T test. So this tells you if there's a significant difference of stressed or not. White blood cell counts, yes, because that's a very small p value. So there is a significant difference here, but not here. No significance in cholesterol. A very significant difference in their depressions, but not in their anxiety and not in their social skills. So that's that part. Please hold. So now we're switching to a different regression model. We're trying to predict high blood pressure in people by looking at their depression scores, anxiety scores, white blood cell count, cholesterol, and their social stuff. So the IVs are the ones that I just mentioned. So we ran it through SPSS. So this is our model one. These are our IVs, our predictors. Our DV is their blood pressure count. So this is your money right here. This R squared tells you what percent of the variance in the high blood pressure in the DV can be explained by your model. 0.13, it's not enough to invest a lot in. So it's kind of a weak model, but I've seen weaker. Okay, this adjusted R squared means that if you did this same test with a different set of people, the R squared could drop as low as that. That means your test is very weak. Okay, so if there's a big change between your R square and your adjusted R square, that means there's something wrong with your model, which we kind of already knew because the R square wasn't very big to begin with. So it ran in ANOVA, and it says no, that your regression is not significant. In other words, your predictors of depression, anxiety, white blood cell count, cholesterol, social interactions are not a good predictor of if a person's going to have high blood pressure or not. So okay, so now we know this is not a good model to predict high blood pressure, but you could look out and see which one of these is the most strongest influencer of high blood pressure by looking at their beta weights. Yes, standardized coefficients are called beta weights, and this tells you who's the more important player. Social interaction seems to be the best indicator because it's bigger. Number 2 comes in at white blood cell count. Number 3 is their depression scores. Number 4 is cholesterol. And the very least effective or the least important when it comes to a person's blood pressure is their BAI, is their anxiety.
Plus or minus doesn't count.
No, doesn't matter if it's plus or negative. It's just negative means when one goes up, the other one goes down. Okay, right? It's just, this is the magnitude of strength. And here's your correlations, partial correlations. They should relatively agree with your beta weights. It basically tells you what percent of the variance each individual IV is contributing to the DV, and they're basically the same as that one. So this is a crappy model. That's what you're going to say. Okay, please hold. Here we go, part 3. So now you're going to use your predictors, depression, anxiety, white blood cell count, cholesterol, social interaction, to try to put each subject into either the stress category or the no stress category. This is called a logistic regression model. Your DV has to be what we call dichotomous. In other words, did they live or die? Did they stay or go? So for you, they're either going to be stressed or non-stressed. That is your DV. So here we go. Logistic regression. We're going to go to analyze, get everything in the picture. Analyze, regression, but get back in there. God dang it. Binary logistic. Your DV is your stress, right? And all these other bad boys are your IVs.
Are they covariates?
Yeah, that's just how we put it in there. You guys, you know what a covariate is?
No.
A
Well, I've heard of it before, but
covariate, it's just something you suspect is influencing the outcome.
okay.
So basically everything's a covariate. All right, we make sure this is there, and we did, okay, we did that, and we did, change now. Click options button. We need the classification pod. These tests here will tell you how strong your case, how strong your model is, right? If your model's weak, forget it. You don't need anything. Click continue. And again, all of this stuff is online. Okay, so then you click OK. Here comes the fun part. Now we're going to interpret your logistic regression model. All right, so you're trying to predict from your IVs whether each subject is going to be stressed or not. So the first table tells us that you got 60 people, nobody missing. Good. Second one, encoding. So no stress is 0, stress is 1. Good. The block 0 is like a base camp. It tells you how good it is predicting without any of the variables involved. So you never look at the block O, right? That doesn't really mean anything. That's this system making a baseline that it's going to compare when you start throwing variables in. So we're going to look at the block 1, okay? So we go to block 1. This is where your IVs are thrown in there. So you look at the chi-squared tests, and wow, good. You got a significant difference in there somewhere. So that means that this chi-squared test, which is a non-parametric test, is saying that, yes, there's a significant difference somewhere between your IVs when it comes to putting people into stress and don't stress. And we already know which ones they are. White blood cell count and depression. Right. Those are your two players.
Okay.
All right, so this is okay, so we're dropping down to the Homer-Lemshow test. So we want the significance to be less than 0.05, and it's not, right. So again, we learned that from your multiple regression that your IVs are not a good predictor of DVs. Your IVs are not strongly related. That's basically what this is saying. So this says that your test is not a good model. In other words, you cannot predict if a person is going to have stress or not by most of your DV, but by most of your IVs, right? Yeah. So only depression and white blood cell count. So this says that it can correctly predict those without stress 86% of the time, those with stress 68% of the time. So your overall percentage of accuracy is about 80%, which actually isn't bad. But again, we don't know if these numbers, we already know that they're not significant. So we know that this is not going to be a very accurate test. And let's see, model summary. Where's model summary? There's model summary. These tests, the Nagle-Kirky test and the Cox-Snell test, they're kind of like, this tells you how much of the percentage of the variance between your yes and no's on your stress can be predicted by this model. So roughly, you always take the bigger number. So roughly 40% of whether they end up in yes or no on the thing can be predicted by your model, which is not as good as a coin flip, right? Coin flip is 50-50, so that means your model is crap. But I think that's about all you got to talk about. So your logistic regression model is not a good predictor.
Okay, so you don't think she'll care whether it's a good or not?
No. You're just going to run the test, and you're just going to come out and say, this, and this means it's not a good. This is not a good model. In other words, your predictors are not good predictors. Okay. So, but yeah.
Well, that happens.
All right. This is me signing out.